So we're going to jump back into this entire process of how a neuron works. By the next step is explaining how does this neuron actually fire off, right? So the last lecture talked about resting potential, and resting potential is the state of the neuron when it is not being used. So the whole point of a neuron is to use it, right? So let's talk about what happens next. The first thing I want to point out to you is this idea that I'm going to bring up several times, is that I really want you to start thinking about the neuron as having two separate components: the cell body portion and the axon portion. The axon portion is where the action potential occurs, but it only is able to occur if the cell body portion dictates that. So we're going to talk about this part second. So I'm basically explaining to you what happens after the neuron gets stimulated, but the second part of this process is how does that neuron get stimulated. But we're going to worry about that a little later on in this unit. But for today, what I want to do is I want to really dive into what happens when this neuron fires off, and that's called an action potential. But first, let's quickly just review this idea of resting potential. So resting potential is when the neuron is not firing off, and that is really dictated by four factors. There's four things that contribute to this value of negative 70 millivolts. The first thing is the idea of sodium being outside of the cell. There's a large concentration of sodium ions outside of the cell, which are positively charged, which makes the outside positive. There is a concentration of potassium ions inside the neuron, which are also positively charged, but there are leakage channels which allow some potassium to leave. And when that potassium leaves, it makes the inside of the neuron slightly negative. So we have our positives outside of sodium, and we have our potassiums inside leaking out, making the inside more negative. We also have these stars here which represent proteins, and these proteins are large bulky molecules that can't get out, but they have a slight negative charge. So those also are contributing to our negative internal value. And then finally, our fourth factor is the sodium-potassium pump. And the sodium-potassium pump lets 3 sodiums out for every 2 potassiums that come back in. And what that does is it maintains that imbalance of charge, where there's more positives leaving than there are positives coming back in. So all 4 of those factors together leads us to this value of negative 70. And that's what's considered resting potential. But now let's say this neuron gets stimulated. Another neuron stimulates it. That triggers this thing called an action potential. And an action potential has multiple stages to it. So I'm going to run through and explain it as best I can, and then I'll back it up in class with some activities and some further instruction. But let's go back to the notes here. So what we see here is the action potential. And an action potential, very simply, is a change in the electrical potential across the cell membrane that occurs after a stimulus. So what does that mean? This neuron gets stimulated by another neuron. And there are really multiple stages to it. So I'm going to explain that now, and then we'll see how this goes. All right, so initially we have a neuron that is at rest, and resting potential is that negative 70 millivolts, and that is considered polarized. And I'm going to be using that term a lot in this lecture. Depolarized, repolarized, hyperpolarized, right? But polarized just means different. So negative 70 on the inside of the membrane and 0 on the outside, and that is polarized. Okay, so I want to use this neuron. So the first thing that happens is that neuron gets stimulated, which leads to something happening. And that thing that happens is called depolarization. So why is it depolarized? Well, what happens is the sodium channels open, and that triggers this whole process. So when the sodium channels open, that allows sodium to start moving into the neuron like it wants to. And when the sodium moves into the neuron, it brings its positive charge with it, and it takes a negative 70 millivolt value all the way up to positive 30. So let me go back to my diagram to hopefully help to explain that. So the first thing that happens in an action potential is the sodium channels open. And when the sodium channels open, sodium floods in. Now, my diagram is not accurate in the slightest in terms of how it actually looks. One thing I want to make sure you understand is that both sides of this membrane would have the channels. I just didn't want to make this thing too confusing. So if there's sodium channels on this side, there's also sodium channels on this side. So a lot of sodium floods in. So as the sodium floods in, what happens to this number is it starts to become more positive, right? Because more positives are coming in. It gets to negative 60 millivolts, it gets to negative 55 millivolts, which we're going to talk about this a little bit later, but that is a very important number. That triggers the action potential. But for right now, we're just going to keep going. So as more sodium comes in, what ends up happening is it goes all the way up to positive 30 millivolts. So much sodium comes in that it actually becomes positive compared to the outside. And because it's getting closer to zero, we're not calling that polarized anymore. We're calling it depolarized because it's becoming less polar. It's going, so if we have zero here, we have negative 70 millivolts. This value is going up. It's getting more positive. So it's getting closer to zero. So much so that it surpasses it all the way up to positive 30. So we're going to call that depolarization because it's becoming less polar. So the first part of this process is the sodium channels open and sodium floods in. And those sodium channels only stay open for a short while. And I'm going to explain that in a little more detail on another slide in this lecture. But that is the first step of this process. Sodium floods in and the cell becomes depolarized. The next step of this process is potassium channels open. So the sodium channels are open for a short period of time, sodium floods in, those sodium channels close, and now the potassium channels open. And when the potassium channels open, potassium floods out, right? And when the potassium floods out, that takes the positive charge with it, making it back to negative again. So it jumps way back down again. So it gets all the way up to positive 30, it becomes depolarized, and then it dives way back down again to negative 70 millivolts. And that is called repolarization because now it's going back to that initial value. So it gets depolarized up to positive 30, and then it gets repolarized back down to negative 70. And the way I think of it is I try to imagine a seesaw in your head. A seesaw, one side goes up, the other side goes down. One side goes up, the other side goes down. There's never a scenario where both sides go up because that's not a seesaw, right? So that's essentially what's happening here. You have a seesaw of sodium comes in, makes it very positive, and then potassium comes in, making it negative again. And that happens all the way down the neuron. So this is not happening at once. It happens in stages down the neuron. And I'll explain that in better detail in a minute. But let's go back to our diagram here so I can pick up where I left off. So at this point, we're at positive 30, right? And that is called depolarization. But now our potassium channels open. And when our potassium channels open, potassium floods out. And when potassium floods out, what does it bring with it? It brings this positive charge, causing this value to go back down to negative 70 millivolts. And we call that repolarization. So if I were to draw this in a graph, which we'll be doing a little later in this unit, you have resting potential, right? That's at negative 70 millivolts. And then the sodium channels open, causing that charge to increase all the way up to positive 30. And that is going to be called depolarization because it is becoming depolarized. And then the potassium channels open, causing that value to dip back down again because of the fact that the potassium channels are open, positives are leaving. We're going to call that repolarization, and that's going to bring it all the way back down to negative 70, which is going to be our resting potential. It actually dips down to negative 90, and we're going to talk more about that later. That's called hyperpolarization. And there's a time period where that neuron is hyperpolarized, but we're going to talk more about that in a little while. For right now, I just want you to know that it gets depolarized and then it gets repolarized. Just like a seesaw, it goes up, it's got to come back down again. Now we have a problem. What's our problem? Well, if you take a look here, this neuron, all the potassiums are on the outside and the sodiums are on the inside. That ain't going to work, right? That's a problem. This neuron would not be able to fire off again if we just left it like this. So thankfully, we have our good friend over here, the sodium-potassium pump. And what the sodium-potassium pump does is it gets rid of the excess sodium on the inside. It kicks 3 sodiums out for every 2 potassiums it brings back in. So think of your sodium-potassium pump as the reset button that gets us back to resting potential. Now my diagram again is not very accurate because there's not one sodium-potassium pump. There's many sodium-potassium pumps all along this membrane. So let's go back to this. One thing I want to point out to you is this is a process that moves down the entire axon. So an action potential doesn't happen at once. It is a process that occurs all the way down the axon. Think of it like whisper down the lane. One area of action potential occurs here, that triggers the next area, that triggers the next area, that triggers the next area. And this moves all the way down the axon until it gets to the end. When there's an action potential happening here, this part of the neuron's back in resting potential. So it's not like the entire neuron gets affected at once. It happens in stages. And again, we're going to move through this at a reasonable rate where you're going to be able to process this information. But I want to finish up here with a couple more ideas. So there's a difference between the sodium channels and the potassium channels. And this is what allows this whole process to happen. Sodium channels actually have two gates on them. They have two doorways. They have a activation and an inactivation gate. Potassium channels only have one gate. So I want you to think of like the front of the high school. A lot of buildings have this. You have like a lobby kind of. Like you have a set of doors and there's a little space there and then there's another set of doors, right? So when you go into the front of the school, you open up the front door and there's this little like entrance area, and then there's a second doorway. That's essentially how these sodium channels are. There's two doorways. What ends up happening is the activation gate opens quickly. So there's two gates, right? There's two gates on the bottom. The activation gate opens very quickly. So it's kind of like this. It's set up like this. It's hard to do because I'm seeing them reverse of myself. What ends up happening is the activation gate opens very quickly and the channel is open. And when that happens, the inactivation gate slowly closes. So it kind of goes like this. This is weird. That's hard for me to do. It goes like that and then like that. Why is that important? Well, what that does is it allows a small amount of sodium into the membrane. It limits the amount that can get in. So some sodium can get in. Potassium channels do not have that second gate. And what that does is it allows more potassium to leave than sodium goes in. And that's an important detail that I'm going to bring up again when I talk about something called hyperpolarization. But the main thing I want you to understand is the idea that there's two channels for the sodium channels. And that's what controls how much goes in to the membrane. So when I show you guys a little diagram of that, I think that'll make some sense. This is just another diagram of this whole process. So basically what you have going on here is you have a resting membrane where you have sodium outside and potassium inside. You'll notice here the action potential does not happen all at once. Down here we still have sodium outside and potassium inside. But at this point the sodium-potassium channels open, sodium floods in, causing depolarization. So you can see that value goes way up to positive 30. And then the potassium channels open, potassium leaves, bringing it back down to negative 70, and we call that repolarization. So this moves all the way down the axon to the end, and that's how it's able to maintain that high level of charge. So I'm going to finish up here with a little animation of this process that I think will hopefully bring this home for you. I like this animation. So what you see here is you see a membrane. You have your potassium channels here, you have your sodium channel here, and you have your sodium-potassium pump. We have our potassium channels closed, our sodium channel is closed. So let's see what happens. We have an impulse travel down the membrane. That's the sodium-potassium pump just kind of keeping resting potential, letting sodium out, potassium in. But now we have our impulse, and that causes the sodium channel open, sodium floods in. We have the inactivation gate close, preventing any more sodium from getting in. The potassium channels open, potassium floods out, bringing it back down to that negative value of negative 70. And then we have our sodium-potassium pump kicks in and puts everything back where it was before, so this can go through another action potential. So this entire process is like a seesaw. Sodium channels open first, sodium floods in, causing depolarization. And then you have our potassium channels opening second, causing repolarization. And then our sodium-potassium pump does the work to put everything back where it belongs. And now it's at resting potential and it's ready for another impulse. Okay, that was a lot, so we're going to finish up with that. Thank you very much.